Writing correct programs is tough, and writing correct concurrent programs is even tougher. There are more things that can go wrong when programs run at the same time compared to running one after another. So, why do we use concurrency? Let's dive into the basics of how Java handles threads and benefits and risks of threads. Let's quickly understand the difference between processes and threads. A process is an independent running instance of a program that has its own isolated memory space and system resources. A thread is a lightweight unit of execution within a process that shares the parent process's memory and resources, making communication faster and context switching more efficient. Imagine a simple Spring Boot application running on an AWS ECS container that exposes a REST API endpoint hello, which returns hello message. When a user sends an HTTP request to your application's URL, usually via an application load balancer, the load balancer routes the request to the running container. Inside that specific container, which is an independent process, the embedded Tomcat server assigns an incoming request to one of its managed request handling threads. This thread executes your controller and service logic. If your application needs to handle background tasks, example sending an email asynchronously, it might spin up additional separate threads within the same process. Once the request is processed, the thread is returned to the pool ready for the next request. In summary, the entire Spring Boot instance within a container is a process, while the concurrent handling of multiple user requests within that instance is managed by multiple threads. This example shows how threads help manage multiple tasks efficiently within a single process, making applications faster and more responsive. Threads are everywhere. Every Java application uses threads. When the JVM starts, it creates threads for JVM housekeeping tasks like garbage collection, along with the main thread which runs the main method. Similarly, in Spring Boot framework, applications also create their own threads for various housekeeping and background tasks, in addition to standard JVM threads. For example, connection pool such as Hikari connection pool uses a dedicated housekeeper thread to monitor DB connection health, manage idle connections, and clean up abandoned connections. If you use these frameworks, which many developers do, it's important to understand concurrency and thread safety. These frameworks create threads and call your code component from them. While it might seem like concurrency is an optional or advanced feature, the truth is that almost all Java applications are multi-threaded. These frameworks don't shield you from the need to properly manage access to your shared application state. Now that we have explored why concurrency matters and how threads power Java applications behind the scene, it's time to bring these ideas to life. Let's dive into a simple yet powerful example, building a small application that generates a ticket ID. This hands-on demo will show you concurrency in action. Let's look at what happens when we run the ID generator application in two different ways. First, we'll see the results when the application is triggered sequentially, one request at a time. So our application is up and running. It's running on port 8080. Let me trigger this API. So firstly, we got ticket ID as 1. Let me re-trigger it. Now we are getting 2. It's working as expected. Now let's dig deep into this. So if we check the logs, let me expand this. Okay, when we triggered the API, it initialized this the dispatcher servlet, right? Once the initialization is complete, it handled this request. Okay, so each incoming HTTP request is picked up by a thread from Tomcat executor pool. Okay, so the first request handled by this thread HTTP neo 8080 exec1, and second HTTP request handled by this HTTP neo 8080 exec2. If you set more requests, you will see exec3, exec4, etc. depending on concurrency and pool size. In Java, threads are organized into thread groups. By default, unless you create a custom group, all application threads, including Tomcat worker threads, belong to main group. Now let's understand the meaning of HTTP neo 8080 exec1. This prefix HTTP indicates the protocol being served by the Tomcat connector. This neo, which stands for non-blocking IO, is a Tomcat connector type. With non-blocking IO, fewer threads can handle thousands of concurrent connections, making your application scalable and efficient. 8080 is the port number your application is listening on, and exec1 is the worker thread from the Tomcat executor pool. Now we'll simulate 100 users triggering it simultaneously using Apache JMeter to see how it behaves under concurrent load. So I have this Apache JMeter test plan created for 100 concurrent connections at a time. Let's run this. So it's running, it's done. Let's check the logs again. So you will notice here the order of operations across multiple threads are unpredictable and surprising. While the application works perfectly fine in single thread environment, it doesn't behave the same way when multiple threads are involved. The core issue with the ID generator is that, due to unlucky timings, two threads might call the getTicketID method and end up receiving the same value, like this. Now just imagine, what if this ticket ID is primary key for your DB? This would cause a great deal of chaos, right? Although this increment operator looks like a single step, right? ID plus plus. It's actually made up of three separate actions, which are reading the current ID, adding one to it, and then writing new ID back. Because threads can be interleaved in any order by the runtime, it's possible for two threads to read the same value simultaneously, both add one and both write back the same incremented value. This leads to duplicate ID issue, which is a problem in concurrent environment. This example illustrates a common concurrency problem known as race condition. For a multi-threaded program to behave predictably, access to shared variables, in this case ID, must be carefully coordinated so that threads don't interfere with each other. Now let's move on to some final thoughts to keep in mind as you write your own concurrent code. Like many concurrency bugs, issues that cause failures can be tricky to find because they depend on the timing of events in a different threads. This means they might not even show up during development or testing. In well-designed concurrent applications, using threads can improve performance. However, threads do come up with some runtime overhead. One of them is context switches. When a scheduler pauses one thread so another can run, this happens more often in applications with many threads and carry costs like saving and restoring execution state, losing cache locality, and CPU time spent managing threads instead of running code. All these add to performance overhead. Developing, testing, and debugging multi-threaded program can be very challenging because concurrency bugs don't always appear consistently. When they do, it's often at the worst possible time in production under heavy load. That's why this playlist it is designed to help you build correct and efficient concurrent applications in Java. By consistently following best practices, you will create concurrent applications that are both reliable and maintainable. That's all for this first introductory video on concurrency. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.